Imagine building a house, laying the foundation, framing the walls, and raising the roof. But not on Earth, where gravity and atmosphere are givens. In space, all the rules change. The familiar laws of physics that govern our lives here on Earth take on entirely new dimensions. There's no ground, no solid foundation to build upon, no air to breathe or sustain life, no protective sky to filter out harmful radiation, and no gravity. Everything floats, unbound by the forces we take for granted. The sun's rays are deadly, unfiltered, and intense, and the vacuum outside is unforgiving. It's a hostile environment that demands respect and innovation. Building a home in space means creating an entire world from scratch. It's about engineering a livable environment where none exists naturally. A space habitat isn't just a shelter, it's more than just a place to sleep. It's a self-contained ecosystem, a miniature Earth, a delicate balance of systems working in harmony. It must generate air, providing a breathable atmosphere, recycle water, turning waste into a vital resource, grow food, sustaining its inhabitants with a closed-loop system, and shield its inhabitants from radiation, protecting them from cosmic dangers. And it must solve the problem of gravity, perhaps through rotation or other innovative means. So, how do we design such a place? We turn to physics and engineering, pushing the boundaries of what's possible. The dream of living among the stars, once relegated to science fiction, is a puzzle of science and ingenuity, a challenge that demands creativity and precision. Space architects aren't just drawing buildings, they're designing entire ecosystems. They're designing life support, ensuring the survival of those within, radiation shields and artificial gravity. They are crafting a new reality. Every resource is precious, nothing can be wasted. Efficiency and sustainability are paramount. On Earth, we build with certainty, relying on the stability of our planet. In space, we create from nothing, conjuring habitable spaces out of the void. The difference? On Earth, it's construction, a process of assembling pre-existing elements. In space, it's creation, a fundamental act of bringing something new into existence. Every blueprint is a leap of imagination and technology, a testament to human potential. The challenge is not just to survive, but to thrive, to build communities and cultures beyond Earth. Our future in space depends on mastering these new rules, adapting to the unique challenges of this environment. The first step, rethinking what home really means. It's not just a place, but a concept, a feeling, a community. In the void, we must become creators, not just builders. We must be architects of our own destiny. This is the new frontier of human habitation, a challenge and an opportunity to redefine what it means to be human. Early visions of space living were bold, dreams of escaping Earth's confines and building new homes among the stars. Entire cities floating in the void, self-sufficient ecosystems orbiting distant planets, a testament to human ingenuity and our boundless ambition. To make these worlds possible, designers turned to three classic shapes, fundamental geometric forms that offer unique advantages in the harsh environment of space: the sphere, the torus, and the cylinder, each a potential building block for a future among the stars. These forms weren't chosen for looks, though their elegance is undeniable, but for their inherent strength, their structural integrity, and their ability to create artificial gravity, a crucial element for long-term human habitation. The Bernal Sphere, named after physicist John Desmond Bernal, a giant hollow ball with people living on the inside equator, utilizing centrifugal force to simulate Earth-like gravity. Sunlight piped in by mirrors, carefully angled to provide natural light and warmth. Its compact, strong shape holds air like a balloon, making it an efficient and reliable design, and creates a cozy, self-contained world, a miniature biosphere where life can thrive far from Earth. The Stanford Torus, a design conceived during a 1975 NASA summer study. Imagine a spinning donut, a mile across, a colossal ring of habitable space. People live on the inner ring, feeling gravity as the structure spins, creating a comfortable and familiar environment. Walk far enough, and you'll circle the whole world, experiencing a unique sense of community and connection. Sunlight is reflected in by mirrors, creating day and night, and allowing for agriculture and plant life. The O'Neill cylinder, named after physicist Gerard K. O'Neill. The most ambitious, miles long, with entire landscapes inside, capable of housing millions of people. 2 cylinders spin in opposite directions for stability, ensuring a balanced and controlled environment. People live on the inner surface, experiencing gravity similar to that on Earth. With clouds, weather, and a sky that's actually the other side of the cylinder, creating a truly immersive and natural-feeling environment. Huge windows and mirrors control sunlight, simulating a 24-hour day and allowing for diverse ecosystems to flourish. These aren't just habitats, they're artificial worlds, miniature planets capable of sustaining life for generations to come. Each design solves the problem of gravity and space in its own way, offering unique solutions to the challenges of off-world living. They're blueprints for humanity's future among the stars, a vision of a multi-planetary civilization. The dream, to build not just shelters but new Earths, vibrant and thriving ecosystems where humanity can flourish. These classic shapes are our first steps toward that dream, the foundation upon which we can build a future among the stars. Living without gravity presents a unique set of challenges. The human body, so accustomed to Earth's pull, faces significant difficulties in a zero-gravity environment. Bones weaken, losing density at an alarming rate. It's a bit like accelerated aging for the skeletal system. Muscles waste, as they no longer have to work against gravity to maintain posture and movement. Fluids shift, redistributing throughout the body and causing a puffy face and other physiological changes. To survive long-term in space, and to truly thrive beyond Earth, we need artificial gravity. It's not just a luxury, it's a necessity. The most promising solution? Spin the habitat. Rotation can simulate the effects of gravity. Centrifugal force pushes residents outward, mimicking the sensation of weight and grounding, effectively simulating gravity, allowing people to walk, run, and live much as they do on Earth. The floor becomes the inner wall, the familiar ground we take for granted. Down is away from the center, towards the outer rim of the spinning structure. It's a fundamental shift in perspective. The right spin speed is crucial for comfort and well-being. It's a delicate balance. Too slow, and the artificial gravity is weak, offering little benefit. Too fast, and people get dizzy, experiencing motion sickness and disorientation. Larger habitats, like the O'Neill cylinder, can spin slower and feel more natural, minimizing these side effects. But gravity isn't the only challenge we face in creating habitable space environments. Space is filled with radiation, a constant bombardment of energetic particles and micrometeoroids, tiny but potentially damaging projectiles. On Earth, our atmosphere shields us from much of this radiation, and our planet's magnetic field deflects charged particles. In space, the habitat's hull must do the job of both atmosphere and magnetic field, providing comprehensive protection. Thick walls of rock, metal, and soil can absorb radiation and protect life inside, creating a safe haven from the harsh realities of space. Every design must carefully balance gravity, radiation safety, micrometeoroid protection, and of course, human comfort. The underlying physics is relatively simple and well understood, but the engineering required to bring these concepts to life is monumental in scale and complexity. Building a spinning, shielded world is undoubtedly one of humanity's greatest engineering and logistical challenges, but it's the only way to make space truly livable, to create thriving communities beyond our home planet, and to secure a future for humanity among the stars. Each classic habitat offers a different vision for life in space. The Bernal Sphere is compact and efficient, strong, but with limited living space. The Stanford Torus offers more room and an open landscape, but is harder to build and light evenly. The O'Neill cylinder is vast, enough for weather and ecosystems, but requires immense resources. Spheres are economical for small outposts. Toruses feel more like a world. Cylinders are the ultimate dream. The bigger the habitat, the more natural it feels, but the harder it is to build. Each design is a trade-off between efficiency, scale, and human experience. The sphere and torus may be our first steps, the cylinder, a goal for the far future. Choosing a design means balancing ambition with practicality. These debates shape our path to the stars. Every choice teaches us more about building new worlds. The journey is as important as the destination. Today, we're not building giant spinning cities. We're starting small, with modules. Think of them as space Lego bricks assembled piece by piece in orbit. Companies like Axiom Space and the Gateway Foundation are leading the way. Axiom Station will grow by adding modules to the ISS, then become its own station. The Von Braun station starts with a ring, adding modules for hotels, labs, and homes over time. This modular approach lets us build flexibly as demand and funding allow. We can't launch a city in one go, but we can build it step by step. Rockets carry manageable pieces in space. We assemble something far bigger. Modularity is practical, powerful, and lets us start building our future now. Each module is a lesson, a test, and a step toward larger habitats. The age of modular space living has already begun. Starting small isn't giving up on big dreams. It's the smartest way forward. Launching material to space is expensive. Modules let us manage cost and risk. Each new module is a chance to test technology and fix problems before scaling up. The ISS proved this works. Built over years, it taught us how to live and work in space. Modularity means flexibility. Add, upgrade, or reconfigure as needs change. A modular station can evolve for science, industry, or exploration. Giant monolithic habitats can't adapt as easily. These small stations are our training grounds for the future. Here we learn the skills to build bigger, more ambitious worlds. The journey to a spinning city starts with these first careful steps. Modular outposts are waypoints, not the final goal. They're how we learn, adapt, and prepare for the stars. Every module brings us closer to the dream. Why dream of homes in space? Because designing them is about more than engineering. It's about imagining our future. Space habitats are blueprints for survival, hope, and human curiosity. Building a world in space forces us to value and replicate what Earth gives us for free. The science of habitats is also the science of sustainability, lessons we can use on Earth. These designs inspire new generations and push the limits of what's possible. Even if we never build a giant cylinder, the effort sparks innovation for all humanity. Every step forward is a leap for our species. As we study and build, we prepare to leave our cradle. Whether in a small station or a spinning city, our journey starts now. We dare to imagine, to solve, and to explore. The cosmos is waiting, and we're ready to call it home.